We're about to start. It's my great pleasure to introduce this year's recipient of the Test of Time Award, Lin Xiao. So the Test of Time Award is given to a paper that appeared at NeurIPS 10 years ago, a paper that stands out as having had a significant and lasting impact on the community. And this year's award went to Lin Xiao. Lin is a senior principal researcher at Microsoft Research. He received his PhD from Stanford and did a postdoc at Caltech. His current research interests include large-scale optimization and machine learning, randomized algorithms and parallel and distributed computing, and he has made many contributions to online learning and stochastic optimization.
Thank you. Thank you. Yeah. I thank the committee for the award. It's a great honor for me to be here today, and certainly a very humbling experience to receive this award. First of all, I would like to say that I'm very grateful to Microsoft, especially Microsoft Research, an amazing organization and all the great people that built such an excellent research environment that made this work possible. I also would like to acknowledge the influence and inspiration of Professor onlineconvex on this paper. Actually, pretty much everything in my research. In particular, this work is a simple extension of his paper on primal dual subgradient methods for convex problems, published also in 2009. Of course, I read the report version in 2005. There's no doubt that we are at a very exciting time of machine learning. Now, this year, the Turing Award went to 3 distinguished researchers of this community. Back then, 10 years ago, the conference was much smaller, but I think I felt it was just as exciting as a relatively younger researcher, of course, for different topics. Actually, several of the very exciting topics at that time clashed together to create the motivation of this work. So for the background, I will summarize each one of these topics by a single slides, and then I'll go over the main result of the paper and then some further development in the last 10 years. I will finish with some final reflections. The first topic is a stochastic gradient descent. Here, W is the optimization variable. In machine learning, we call it weight vectors. Z is a random variable, which represents data. And here we would like to minimize either the population risk or the empirical risk of a very large sample. SGD adjusts the weight vector by using a single stochastic gradient evaluated at a sample ZT, or you can see the mini batch. And it's well known that this work goes back to the seminal work of Robbins and Monroe, and several of the variations, like momentum with adaptations, has become the workhouses of machine learning, especially for deep learning today. In fact, last year's Test of Time Award was given to a paper by Balto and Bosquet on why SGD is the method to go for large-scale machine learning. For this talk, we'll need some simple convergence theory. Basically, depending on the loss function f is convex or strongly convex, you could have 1 over square root t or 1 over t convergence rate. The step size, alpha t, actually diminishes with a similar rate. Another very exciting topic was online convex optimization. Here we consider an online game where the player predicts a vector wt at each iteration, and then it will receive a convex loss, arbitrary convex loss function, and suffers a loss of ft evaluated at wt. Here we do not assume any probabilistic assumption on the functions. It could be adversarial. The measure of performance in this case is called regret. It's basically the difference between the cumulative losses of the player's algorithm and the total loss of a fixed W from hindsight. It turns out that the efficient algorithms for this is very similar to SGD, and we could have like square root T regret or log T regret using online to batch conversion. If you divide them by T and assume stochastic distributions, then you can have this same convergence rate at stochastic gradient methods. At that time, yet another very, I think many of you still know that extremely hot topic was compressed sensing. One of the most famous examples is the lasso. We want to minimize a quadratic function with constraint on the L1 norm. And it's often very convenient to consider a unconstrained version where you have a L1 regularization instead of constraints. So in this picture, the black dot is the minimum of unconstrained minimization, and the green dot is minimization with L2 norm constraints. It touches on the sublevel set. And the red dot is a solution with L1 constraints. As you can see, with L1 constraints, it's more likely it will end up on the coordinate axis. So if many coordinates is like this, you will have a very sparse solution. And there's lots of theory in compressed sensing developed from roughly 2004 and so on. And it also has generalizations in low-rank matrix completion with the nuclear norm regularizations. And there's many different types of algorithms for solving this problem. And the most relevant here is the proximal gradient method. I will go to more detail. So for this case, we minimize a smooth function f and a non-smooth function psi. If you add them up, it will still be a convex, but non-smooth. So the classical method for solving this problem is subgradient method. Here, causality is a subgradient of paucity. Equivalently, you are solving a simple optimization problem at each step. Basically, you take the linear approximation of your function, which is in red, and then the quadratic penalty just restrict how far you can go from step to step, because the linear function certainly is unbounded. But since this approximation is very rough, especially if there's a kink there, you better go back, use a small step size. So the step size actually scales at 1 over square root T. In proximal gradient methods, it basically say we are only going to linearize the smooth function, which is a dotted line, and we add the whole regularization without any change. We'll end up with this blue curve. It's a much better model. In this case, if we just minimize the simple model, we actually get the optimal solution immediately. In general, we can afford to use a constant step size and get a much faster 1 over T convergence instead of 1 over square root T. OK, of course, here we have to be able to solve this problem easily. Often it means a closed form solution. And it can be also written in an equivalent form, which is called forward-backward splitting. Basically, we first take the gradient step of the smooth part, and then compute the proximal mapping of the non-smooth part, with scaled by alpha. For the case of L1, the solution is given by this soft thresholding or shrinkage operator, where if the magnitude of this number of each coordinate is less than alpha times lambda, you set it 0. Otherwise, you shrink this magnitude by the same amount. OK. I hope this very short summaries make sense for most of you. And I think they are pretty active today, these topics. So the motivation I worked on this paper was the clash of them all. You put them together, you want a stochastic streaming or online algorithm for large-scale sparse optimization. So this is more kind of a formal formulation. Now the smooth part, is the loss part is population risk. or you can replace that with empirical risk also. Since the function is stochastic, non-differentiable, the classical stochastic subgradient method will still work. Here I use GT as a shorthand to the subgradient of f. And then the step size is 1 over square root t. Here, there are two sources of slow convergence. One is non-smooth regularization. As we can see, we can use proximal tricks to make it go away. But the second part, stochastic gradient, seems to be intrinsic. You can, it has to be 1 over square root t convergence, slow step sizes. But this is OK, as shown by the paper by Bosquet. This is sufficient for machine learning. But here, our main concern is sparsity. So with L1 and with this diminishing step sizes, can we still get desired sparsity patterns? Of course, the most obvious idea is to extend the proximal gradient method in the stochastic setting, where you just replace the gradient with the subgradient GT. Another change is that the coefficient of the quadratic penalty is 1 over alpha t. That goes to, you have to use smaller step sizes. Then you can show it actually converges. In this case, the update for L1 is this shrinkage operator as I showed before. But remember, you need to scale the threshold lambda by the step size. And when alpha goes on and on, goes to 0, you may not get enough thresholding. So if you run an experiment, you see, oh, the the weight I got is not sparse. So RDA is basically to replace that single linear approximation with the average of all the linear approximations from the beginning. And the second important difference is the coefficient on the quadratic penalty now becomes smaller and smaller, meaning you can use larger step sizes. And we can remove those constant terms. We're just using this GT of bar as the average gradient, so that's a simpler form of as RDA. But now, if you write down the L1 solution, it is this shrinkage operator. Now the shrinkage is lambda on the average gradient. There's an initial point as well. But there's weird scaling of square root t. You can multiply it inside. This more strange thing happened. Now you are thresholding within a larger threshold, which is very counterintuitive in stochastic optimization. But you got really sparse solution. So, okay, so in general, you can use a beta t there. If it's convex, you can say beta t equals square root t. If the regularization is strongly convex, you can set beta t equal to 0. You do not need any penalty. And if you let the psi equal to 0 on the indicated function for the convex set, this recovers Nesterov's dual averaging method. Now you can see this is really a very simple extension of Nesterov's work. But it's a very interesting one, because with the indicator function, either 0 or infinity, you will never be able to see the drama of the scaling. T, square root t, or t, 1 over square root t, those doesn't exist. Okay, now the boring part is the standard theory, the regret for online convex optimization or stochastic optimization. They all have the same rate as classical subgradient methods. Okay, I'll just show you the original experiment in the paper. It's on binary classification with the logistic regression on MNIST data set. Here, we just show the solution after, 10,000 iterations with different methods, with different regularization strings lambda. In the middle, we have the solution by interior point methods. I really want to get 8-digit accuracy to see how many number non-zeros are there. So the background gray is 0, and the black dots are the negative, white are the positive. You can see that RDA has much more crisp picture. That means lots of sparsity. And it's more clear to see from this picture. The blue or black line means the number of non-zeros for RDA. The other red or blue are for different variants of a proximal SGD method. The bottom row, you can see the regularization strength is lambda equal to 10, is relatively strong. Now you see there's only like 10 non-zeros, clearly from the very beginning. So even with stochastic gradient method, you can get very sparse solution from the beginning, always. And this is a pairwise classification. Here, on the right top corner is basically comparisons of RDA and the solution of interior point method. There I compare the number of non-zeros and also compare the testing error on the data set. They match pretty much exactly, which is still surprising somewhat. Okay, I think this finished the main result. I will just summarize a few slides, some of the further development on this topic. The first one is a very interesting interpretation by Brandon McMahon. So here's RDA. We can multiply everything by t. See, multiply everything by t. You get sum of the linear models plus t times the non-smooth model, and plus a quadratic. Indeed, he showed that the proximal SGD, what does is that still have the sum of the linear models. But for the t times regularization, it's split into two parts. One is t minus one of the version replaced it by a subgradient, like a linear model, but only keep one of them for the full model. That's why when you do the regularization, you actually get a t times difference. That's why when you do thread shooting with the proximal SGD, you get a 1 over square root t thread shooting. But with RDA, you get a square root t times the thread shooting. So that's a very interesting interpretation. And of course, he developed a hybrid. One thing is that the proximal SGD has this, the quadratic penalties has centered around all the different points. It has some advantage in practice, can show a faster convergence. So if you combine them, you get the best of both worlds. But of course, in theory, they're still the same convergence rate. At that time, I didn't, we only observed experiments really gives sparse models, but I wasn't able to prove sparse recovery, which was very important in compressed sensing literature, saying, just prove this is absolutely recovers sparse sport. This work was done by Lee and Wright under some stronger assumptions. Sufficiently large T, you will have this kind of effect. And also, you can develop accelerated versions and ADMM versions. And also, dual averaging has some also very interesting advantage in distributed optimization, not necessarily regularized, and many others. But before I end, I want to mention just the last thing I want to mention is called adaptive RDA. It's basically replace that quadratic term with a diagonal or full matrix if you want, but it's diagonal matrix. And those diagonals are done by the norm of the gradient on that particular coordinates. This is called AdaGrad. I think it's very popular later in deep learning, and eventually the variants of called ADAM. They are very powerful. But here is, in their paper, they have a RDA version of this, supposed to be very good for sparse. But it has not. I have to mention that McMahon also has summarized, extended the different versions of this kind of adaptive ones. But the problem is we have not seen this RDA in deep learning is because, I guess, mostly because you can see the averaging thing works from the beginning. It works definitely for convex models. For non-convex, we don't know. I have not tried. Maybe if you look at it, it will still work, but that one I don't know. So this brings me to the question, what about the non-convex optimization? Non-convex stochastic optimization now is very active in recent years because of deep learning, of course. And I would say the algorithm theory has been relatively well developed for generic problems. In theory, you can use the proximal gradient version with L1, still works. But of course, you're going to worry about maybe not desired sparsity patterns. So the question, would variance of RDA work for non-convex optimization? In fact, there's very recent work shows that RDA works really great for sparse convolutional neural networks, getting very sparse, like 5% on CFR 100, those kind of things. And of course, you will need group lasso to induce structural sparsity. It doesn't make sense just to random sparse in a neural network. The other potential alternative I'd mention is a variance reduction. If you know about the variance reduction techniques, you would notice the similarity of the ideas RDA and this variance reduction. And SAG, SVRG, Saga, all this variance reduction, they all have their proximal extensions, and also to non-convex versions. Some of the aspects in the literature, the major goal in the literature was to show that it sometimes can achieve much faster convergence. But here, I would argue that one of the most important features of this work is that you can actually use a constant step size, even in the stochastic case. This might help you to do a sparse optimization. But I have not tried them. Finally, I think that the motivations for RDA remains valid today. Because on one side, we know that stochastic gradient online algorithms are the mainstays of machine learning, just because with the amount of data we process. On the other hand, I believe sparsity is essential if we would like to scaling up the larger and the larger models. Somewhere, somehow, sparsity has to be an effective part. And of course, we have additional challenges today. As I mentioned before, non-convexity. But also, we have a more complex, or I would say, more structured models. There's a chance to explore the structure. Maybe we can get better solutions. So with this, as always, now I believe the exciting progress is always lying ahead. Thank you.
Thank you very much. There's time for a few questions. There are microphones in the aisles.
Hello. Just a quick question. Thank you very much for the talk. So I just wanted to see if you have some insight how to deal with non-convexity.
What?
To deal with non-convexity?
For non-convexity?
Yes.
You mean the sparsity in non-convexity?
Yes, yeah.
I think, let me say this. I think locally, they're all very similar to convex problems. The most important thing is how is the process you get to the local minimum. So it doesn't make sense to use all the average of the gradient from the beginning. You might want to restart, periodic restart of those kind of variance reduction techniques or RDA type methods. So when you're near a local minimum, then the local theory should be very similar.
So my point is, when the cost function is not convex, then how do you guarantee we can find local minimum, like global minimum?
Okay, local minimum depends on how defined. You can define that the gradient or the gradient mapping equal to 0 in the regularized case. That's usually the definition of a local minimum. Of course, I think recently there have been lots of work on using overall parameterization. Then in lots of the deep learning cases, all the local minimum you got is actually pretty much very close to global minimum anyway.
Thank you. Thank you very much.
Thank you very much. There is a short break now, and we'll resume after 4 o'clock.